Okay, in this video lecture, we're continuing talking about our frequency response for systems, or the transfer function for a system. And we said that we could graph that frequency response in what are called Bode plots. So what is a Bode plot? We actually have two types of Bode plots. One is graphing the magnitude of our system's transfer function, and one's graphing the phase angle. So our magnitude graph is when we take our system g of s and we've replaced s with j omega instead to look at the frequency response we said. And we take the magnitude of that, these bars just mean magnitude or absolute value, and then we put that in decibels. So we take 20 times the log base 10 of that number. So putting it in decimals gets us a kind of logarithmic scale. And our x-axis here is then going to be frequency, and while it's not in decibels, it is in powers of 10. Remember we said our 1 milli really means 0.001, and similarly 1 killi means 1,000. Our Bode phase plots are graphing the phase angle of our transfer function, the symbol I'm meaning to mean phase angle, in degrees. It's not on a logarithmic scale on the y-axis, but it is on a logarithmic scale in our x-axis because we're still doing frequency in powers of 10. So each power of 10, where you increased by 10 times each interval, equals what we call a decade. So a decade normally means 10 years, and here it's going to mean we increased frequency by 10. So from 1 milli to 10 milli, 10 milli to 100 milli, 100 milli to 1, right? Similarly, we increased by 10. We can analyze our Bode plots by some general rules. So in our magnitude plots, so this is magnitude, and this one was phase. Our magnitude plots have the rule that they will have a slope at higher frequencies that equals negative 20 decibels per decade times n minus m, where n is the number of poles from your system's transfer function and m is our number of zeros. So in this here, going from about 1 to 10, I went from about 0 to negative 20 decibels. So I had a slope here of negative 20, went down 20 decibels per power of 10 per decade, right? So from 0 to negative 20, from negative 20 to negative 40 is when I hit a new power of 10 in frequency, and from 100 to 1,000 hit another power of 10. So I can find that slope just if I know my number of zeros and my number of poles. That slope only happened at higher frequencies. We'll talk about when this starts to happen based on our equations from it. So our slope goes up at a magnitude of our pole and it goes down at the magnitude of, I flipped this up, goes down at the magnitude of our pole, goes up at the magnitude of a zero. We'll see that. Our phase plots have an asymptote at negative 90 degrees times n minus m, where again, n's our number of poles, m's our number of zeros. So see, this started at 0, and then it's going to in an asymptote down here about negative 90. And it would reach that negative 90 if I had like one pole and no zeros, or if I had 2 poles and 1 zero. The difference in that had to be 1. If I had 2 poles and no zeros, then I'd have 2 for n minus m, and that times negative 90 would mean I should be going down to negative 180. So we'll use these rules to analyze our Bode plots, but we'll actually see why they work from examples here. So we had started in our class lectures this week with a plot of a differentiator, which is really just a transfer function that equals s, right? Multiplying n by s really differentiated something. So how do I make its frequency plots or its Bode plots? I replace s with j omega. So in place of s here, I get j omega. And what is the magnitude of that function then? Well, our magnitude of that would just equal omega. Again, you could plug it into your square root of a squared plus b squared over the square root of c squared plus d squared to get that magnitude. So if it's just omega, and I'm graphing versus omega, because that's my frequency, right, or my x-axis, then I'm going to have looks like a straight line, I would, right? Kind of like the line y equals x. Y is my magnitude, and this is x from it. But I can plug in numbers and check. So at 10 to the negative 2, for my frequency, when omega equals that, then I'd be plugging in 10 to the negative 2, and that would equal it here. I need to get my magnitude. My magnitude would just equal 10 to the negative 2, but I need it in decibels. So to put it in decibels, I would be taking 20 times the log base 10 of 10 to the negative 2. This logarithm expression evaluates as 10 to what power would equal 10 to the negative 2? Well, what power would that be? That would be negative 2 times 20. So that is negative 40 decibels. So at 10 to the negative 2, I'm going to be at negative 40 decibels. What would I be at 1 when omega is 1? I would have my transfer function then would just equal 1. Put it in decibel form. 1. 10 to the what would equal 1? That would be 0. Right, so 20 times 0 just gets me 0 decibels. So at 1, I will be at 0. In between, if I was at 10 to the negative 1, you could plug in and figure out that you'd get negative 20 decibels. And what would I be 2 decades higher, going up to 10 to the 2? If omega now equals 10 to the 2, then the magnitude of my transfer function equals 10 to the negative 2. And put it in decibels, 20 times log base 10 of 10 to the 2. That evaluates as 2 times 20. That is 40 decibels. Okay, so I should have a straight line if I could draw that straight. And what is the slope of that line? For each decade going by power 10, 10 to the negative 2 to 10 to the negative 1, increased 1 decade, I had a slope of 20 decibels, went up 20 decibels per decade I changed in frequency. From 10 to the negative 1 to 1, that's an extra power of 10, going to 0.1 to 1, right? That went from negative 20 decibels to 0. If I did to 10 to the 1, this should be up to 20 decibels. Halfway between that. And from 10 to the 1 to 10 to the 2, I got up to 40 decibels. So my slope, due to my Bode magnitude rule, should equal 20 decibels times n minus m, where how many zeros and poles did I have there? Oh, I had negative 20 decibels, sorry, times that. Negative 20 decibels n minus m, so make sure I write that correctly. N's my number of poles. M is my number of zeros. In this function, I have no poles. I have no denominator, so there are no values of s that would make the denominator 0, which is a pole. So I will have negative 20 onto 0. I have 1 0, though. This is like my numerator if I put it like over 1, right? This would be the same thing as a fraction over 1. So I could say I have 1 0, which means I have negative 20 onto negative 1 is positive 20, so hence a positive 20 slope. What about my phase angle? My transfer function equals j omega. What is the phase angle of that? Well, how do I evaluate the phase angle? It is the inverse tangent of my imaginary, which would be omega, that's my imaginary magnitude, over my real, which I have no real on this numerator, so it's 0. Technically minus the inverse tangent of my denominator's imaginary, which would be 0, but over 1, like you have a 1 again on the denominator of real. Don't forget, if it doesn't look like a fraction, it really has a 1 on the bottom. It doesn't have 0. This would evaluate to 0, though. I have 0 angle for that. What would this tangent come out to? Well, you may be like, I don't know. I can't plug in an omega. I have to do it for different ones. But if omega is just a constant value and this is 0, where does that inverse tangent always then have to be? Remember, when you're doing that, you're really graphing your complex numbers as real and imaginary. Real is the x-axis, imaginary is your y. And this would end up with 0 real, so I'd have no x-axis value, but up positive omega number of j's, right? That's what this function would be. What angle is that from your positive real axis? That's how we're always evaluating that phase angle. That is positive 90 degrees. So if you just have a positive j value, like I do here, omega j, then its phase is positive 90 degrees. Now that doesn't work if it's a complex number. If I have a 0 plus positive j. What if I had a 0 minus j? That would be down here at negative 90 degrees. So if you have 0 real minus j, that's a phase angle of negative 90. So my phase angle here is just going to be positive 90 degrees. It does not change no matter what that omega is, right? It would just scale up from being 2j, 3j, 4j, just move further up my y-axis, but that doesn't change my phase angle. So for any frequency or x input, it would still have a phase angle of 90 degrees. You could plug in numbers for frequency, like 10 to the negative 2, and check that for yourself. But it does help because your calculator probably won't be able to calculate doing an inverse tangent of over 0 because it thinks that's infinity. So you do need to know what just an imaginary number phase angle is, if it's positive or negative imaginary number. Okay, so that's a differentiator. It's Bode plots. What about an integrator? To integrate, we divide by s, right? If we multiplied by s to differentiate, then it makes sense we divided by s to integrate. So 1 over s is going to be our transfer function. Look at its frequency response. I plug in instead of s, j omega. Okay, and then what is the magnitude of that? Magnitude of that ends up being 1 over omega if you plug it in. Okay, so I expect that to have a graph of what? Magnitude versus frequency. As frequency increases, magnitude is going to decrease. It should decrease linearly. At 10 to the negative 2, when omega is 10 to the negative 2, plug that in here. My transfer function becomes 1 over 10 to the negative 2, which becomes 10 to the 2. In decibels, 20 log base 10 of 10 to the 2 becomes 40 decibels. So I start up at positive 40 decibels here. When omega is 1, magnitude of my transfer function now becomes 1 over 1. It's just 1. In decibels, what is 1? That's 20 log base 10 of 1. 10 to the what gets you 1? That's 0. 0 times 20 is still 0, so 0 decibels here. What about at 10 to the negative 2? We're getting the pattern with this, 10 to the positive 2. Then when I plug in 10 to the positive 2 for omega in this transfer function, my magnitude of my transfer function will become 10 to the negative 2 because I'm dividing by it. So in decibels, that is 20 times log base 10, 10 to the negative 2. It's negative 2 times 20, negative 40 decibels. What was my slope here per decade? Again, I'm kind of skipping a decade on the scale here to plug in fewer number points. 10 to the negative 2 up a decade would be 10 to the negative 1. Really, this would be like 0.01, 0.1, 1, right? 10 to the 1, 10 to the 2. For each decade, you would have had to have gone down 20 decibels. I would go 40 to 20 here, to 0 here, to negative 20 here, to negative 40 here. So this guy has a slope of negative 20 decibels per decade. And it's really just this graph I was trying to draw lines to where these points hit. That obeys by my rule that says 20, negative 20 times my number of n minus m. How many poles do I have here? That's the n, that's 1. I have no zeros, so I should have a slope of negative 20. What about my phase angle? What's a phase angle of 1 over j omega? To do that, I take the inverse tangent. My numerator has 0 imaginary, for 1, minus my inverse tangent in my denominator. I have omega as my imaginary component over 0 real. Inverse tangent of 0 is just 0, minus inverse tangent of, what did we say inverse tangent of omega over 0 was? Just did it up here. It's 90 degrees. Except for here I'm subtracting it, so I'm really taking 0 minus 90 degrees. That gets me negative 90. So this will have a constant negative 90 degrees phase angle, that no matter what frequency is, I just get an imaginary component on the denominator that's negative 90 degrees at any frequency. Okay, let's make our system a little more complicated and do a first order system. So now if my transfer function is 1 over some constant t times s plus 1, where do I have a pole here? I have a pole when s equals negative 1t, right? It's when the denominator equals 0. My transfer function to plug in for frequency is going to become 1 over t omega j, plugging in for s j omega, plus 1. What's the magnitude of that? That is 1 over the square root of 1 squared, but it's just 1, plus t omega squared, because that would be my imaginary part. That may not tell me a whole much just looking at that numerically, but if 1 is much, much greater than omega t, then I can approximate this as being very small because I'm going to square it, and so it would just become 1 over 1, and my magnitude of my transfer function would just be 1. If 1 is much, much less than omega t, then my transfer function's magnitude is going to approach 1 over this value wouldn't be much compared to it, so I could approach it as just the square root of t omega squared, which would be t omega or omega t. My transfer function was 1 when 1 was much, much less, much greater than my imaginary component of the denominator here. What's 1 in decibels? That's 0 decibels. This meant that omega, if I solve for this, omega was much, much less than 1 over t. So on my omega, my x-axis graph, that's frequency, that's omega. When I'm at 1 over t, if I'm much less than that, I will basically be at 0 decibels, not changing much from that, so it's flat. When it's greater, when 1's greater than omega t, or that means omega is much, much greater than 1 over t, right? Then my transfer function will approach this, which looks like I should be going with the slope down, right? Kind of like my just 1 over omega graph up here that I had, we said slope downward. Now I'm going to plug in just a specific value for t here to do it. So let's just say if t is 1, but it would be the same idea if t is any constant. I'll just change my actual value for that. When I get there, I start to slope down from it. Where does this happen? Where do I change magnitude the most? In my case, that was when omega was equal to 1 over t, which is, this is the magnitude of my pole. Remember my pole was when s was equal to negative 1 over t, and you're really plugging in s is now j omega. So it's when your frequency, think of s like frequency, equals 1 over that t value. When we had our transfer function that we said was a first order system from class last week, 1 over RCS plus 1 was our low pass filter as a circuit. If we remember from sensing and measurement, that had a cutoff frequency at 1 over RC. Like RC here is like my T from it. And that cutoff frequency was where when we graphed on a log-log scale, omega again being our frequency, and our y-axis in decibels, that it went from basically being flat to curving down. And what slope will it be curving down with? I have one pole, no zeros, so at negative 20 decibels per decade. Cool. What about phase? Phase is a little more complicated. So the phase angle my transfer function, g of j omega, evaluated for frequency, will be what? Inverse tangent of my numerator, its imaginary component is 0 over 1. Again, that just is 0 degrees. Minus my inverse tangent of my denominator has the imaginary component that is omega t, the real component that is 1. Okay, or just inverse tangent of omega t. Now that's a little harder to evaluate, but if 1 is equal to omega t, then this would be the inverse tangent of 1. I would be at 45 degrees. Okay, if my 1, my real part, right, the real part of my denominator here was 1, the imaginary part of it was omega t, is equal to 10 times my imaginary part, which was omega t. So this is real part of denominator equals 10 times the imaginary part of my denominator, or again, looking for that pole. Then what would omega be for this? Omega would solve to 1 over 10t. And if that real part was much, much bigger than this would practically be like 0 compared to that 1. And the inverse tangent of 0, right, is 0 degrees. So I'd be starting at 0 degrees if omega is less than a value of 1 over 10t. But what happens when I get the reverse? When my imaginary component, which was omega t, equals my real times 10. So here's my real times 10. So this is when imaginary equals real times 10, or my imaginary component is much, much bigger than my real component. Then omega here would solve to be 10 over t. That means this would be much, much bigger than this, and I could approximate it as just omega, and like this was very small or 0. And that would be like you just have an imaginary component, no real. If it's much, much bigger than the real, it's going to be an angle of basically 90 degrees, except I'm subtracting that. Oh, that looks like equals now. I'm subtracting that in this equation. So this is going to get me a phase angle, since it was my denominator, I had to subtract, of negative 90 degrees. Like we saw when this approached, just 1 over omega, that's what that would approach when I assume my imaginary part is much, much bigger than the real if it was plus 1. Look at that. So if I am on my omega graph and I am at omega is 10 over t, I will be at negative 90 degrees. Okay. In the middle, when my imaginary equaled my real, I will be at 45. Okay, so that's when omega equals just 1 over t. I will be at negative 45. That is my inflection point here. So my rule is that I'd get an asymptote at negative 90 degrees for my phase graph times n minus m. Again, n's my number of poles. I had 1 pole here, so negative 90 onto 1 minus no zeros. So slope at negative 90. And my inflection point, where kind of this graph is going to change from one curve to the other, is when my real equaled my imaginary components. In this case, we're talking about my pole. That was for my denominator. And they real equaled my imaginary. Omega had to equal 1 over t, whatever that t value was. If t is 1, that's just going to be at 1. If t is not 1, then that changes. So that's why I wrote them in form of t. So phase is a little more complicated. You start to go down when omega is equal to 1 over t here. And that was because 1 over 10t. That's because my real part was 10 times my imaginary part, so I could approximate it as like it was just real, and that would get me a 0 degrees phase angle. And I start to flatten at my asymptote when omega was equal to 10 over t. That was when my imaginary component, my denominator where I got my pole, the imaginary component was 10 times greater than the real component. So omega t equaled 1 times 10. That's where I start to flatten here. So I get 2 points I have to care about in my phase graph at my actual pole, the magnitude of my pole, right, which was 1 over t. That's where I got my inflection point. A decade to the left of that is where I got this change, and a decade to the right of that is where I got my next change. So useful to know to make general rules about how to draw our systems. If I had the inverse of this first order system, so instead of 1 over ts plus 1, which we just graphed, if I have just ts plus 1, this now has 1, 0, right? No poles. For my Bode magnitude graph, I expect it to have a slope of now, instead of negative 20 decibels per decade, of positive 20 decibels per decade, and it needs to start that slope at the magnitude of, in this case, my 0 instead of my pole. So I start my slope at, when is my 0? So when ts plus 1 equals 0, that is when s, which I'm really plugging in j omega, right? So when omega equals negative 1 over t in its magnitude from that, so I got rid of j. The magnitude of that, then I get rid of also the negative sign, it's just 1 over t. So I never am dealing at a negative point, it's 1 over t. If I had t is equal to 1, then that will be it actually when omega equals 1. So that's where I see this start to slope up at a slope of 20 decibels per decade. So from 1 to 10, that's 1 decade. I went from about 0 decibels to 20 decibels. 10 to 100, I went from 20 to 40 decibels. My phase pot, I started at 0 degrees when my real part is going to be much, much bigger than my imaginary part. It approximates just a real number then, which is 0 degrees. I will have in my phase graph, an asymptote at negative 90 onto my n minus m, which I have now no poles, 1, 0. So that becomes positive 90 degrees. That's my asymptote here. I get an inflection point at 45 degrees from it, where I had my pole, my 0 here. It's inverse of when I had my pole before, it's the same thing. 1 decade to the left of that is where I changed start to make this shift, and 1 decade to the right is where I stopped to reach that asymptote. What if I have a second order system? Can I use my general rules about Bode magnitude and phase plots to graph it? Remember, our general second order system looks like this. Omega n squared over s squared plus 2 zeta omega ns plus omega n squared. Oh, and I was going to write it. That I get corner points in my phase graph when my real equals 10 times my imaginary component of either the numerator or the denominator. Talking about the numerator here since it was a 0 when I had a pole, I was talking about the denominator. And when my imaginary equals 10 times my real components. So we'll use those rules to look at the second order system, which is more complex. So my phase plot and my magnitude plot for a second order system will actually be a little crazier in shape. And I don't expect you to know how to draw these for the second order yourself when they are a crazy second order without easily distinguished real poles. If they're complex poles or they're purely imaginary poles, it gets a little crazy. If I don't have complex poles, then it kind of just looks like my first order system, right? Where I would go down at wherever that pole is. This would be like my critically damped case. Remember when we said when we were critically damped, we get the same pole over again. So we get two poles, but it's really the same pole twice at negative sigma d. The real part of that poles. Okay. If I have, so this critically damped is going to be my blue. My phase graph for that will go from 0. Instead of to negative 90, it will go to negative 180 because I have two poles. So my asymptote now has to be negative 90 times 2 instead of just 1. No zeros. So I expect to be going from 0 to negative 180 in somewhat of a smooth curve there. If I have underdamped cases, though, this gets a little more complex. So if underdamped, I'm going to start with a zeta value equal to 0.5. So remember when you're critically damped, what was your zeta? Your damping ratio. That's when zeta equals 1. From underdamping, will be 0.5. I have to be between 0 and 1, so I'm going to look at it at 0.5 first. My Bode magnitude plot will follow the same shape in general, except for where I was normally used to kind of my break frequency or that pole value. I will get a little hump here, and then it will go down. If I change zeta even more to be more underdamped, so a lower value like 0.1, then I get an even more pronounced hump from it. What will these humps correspond to? They correspond to what's called your resonant frequency of your system. It's the frequency at which they really want to oscillate. If you ever dealt with bridges and dealing with them under winds, there are certain velocities of winds that can make a bridge sway more because it will hit its resonant frequency, because you suddenly get an increase in magnitude of your transfer function at that frequency. Because remember, our underdamped systems were oscillating and dying out. If I have it at a lower value of zeta, it's even oscillating more for longer before it dies out. What about my phase graphs? Well, for underdamped to 0.5, it's going to stay flatter kind of at 0, but then make a more sharper slope to get to 180. And, oh, and I didn't need to draw that as a dot line. We can draw it. I have it in colors, so make it a colored line. If I keep changing zeta to even be lower, I'm going to get an even more pronounced where this starts to be a vertical line in the middle. Still going from 0 to negative 180 because I'm going for a second order system. I have two poles I got to get to negative 180. And if I have no zeros, I'm going to start that at 0 from it. But the shape in which I get that graph changes. So second order systems get a little more complex. I don't expect you to be able to draw those on your own, but you do need to know that as zeta increases, this hump gets more resonant at that resonant frequency, or you can think of zeta increases, getting to critically damped, you lose that hump, because now you're only dealing with real values and not this complex oscillations. In the phase graphs, again, when zeta is 1, that's kind of my inner graph here, and I get a pretty smooth slope going from 0 to negative 180, but I get a much flatter at the top and bottom, or the beginning and end of this graph, as zeta gets smaller to 0.1. 0.1 down here, it really follows this part of my graph. Let's make that a thicker line so I can see it again. Yeah, so it follows like that. Okay, so second order systems get some interesting things going on. Because second order and higher systems are harder to graph by hand for us, we'll learn some techniques on how to do them in the next part of the video lecture. We can use LabVIEW to make them graph ourselves without us doing as much work, right? LabVIEW is nice for that. So we do want to make sure that our graphs in LabVIEW are vaguely correct, even if it's doing the work for us. To use LabVIEW's control design module to make these Bode plots, go under control design, frequency analysis, and then select Bode. That's again the name of our frequency, magnitude, and phase plots. It will graph both. It needs an input of your transfer function, so a state space model that we can make in control design, or we set in our simulation one by specifying those coefficients. And then you can wire a graph from the Bode phase and magnitude outputs of your Bode input here. So that really looks like what I'm talking about. Scroll back up. If I had some transfer function, I wire it to that Bode icon and then to a graph. I thought I'd showed that better there, but I will show it in lab for next week. You do want to check that it's correct though. So always check that in your magnitude graph, you had the correct value approximately at low frequencies. So that's like a G of 0, right? Since you're plugging in G of j omega. Remember we called that like DC gain in sensing and measurement. DC is when our frequencies weren't changing in circuits. So for frequency 0, it's not changing at all. Normally, again, our graphs of frequency don't actually start at 0, but they start at something low, like 10 to the negative 3 or 10 to the negative 2, something. Again, that would be 0.001 and this would be 0.01. You also want to check that its final value is approximately correct when you plug in like infinity for your frequency. So looking at your transfer function at infinity for us, it should be approximately that. So those are a good way to check. So for example, if I have this system 10 onto s plus 1 over s plus 5, I can check what it should look like. So G of 0 for this should get a magnitude when I plug in for S, j omega, and then I'm plugging that in as 0. I'm going to get 0 plus 1 on top, which is 10, over 0 plus 5, which is 5. That's 2. In magnitude, in decibels, right, I got to do 20 times log base 10 of 2. That becomes 6 decibels. Okay. When I plug in infinity for my frequency, a very high frequency, now I kind of have infinity over infinity. Infinity plus 1 is still infinity, infinity plus 5 is still infinity, but I do get kind of still 10 multiplied here. So 20 times the log base 10 of 10, to put it in decibel form, gets me 20 decibels. So I know at low frequencies, low values on my x-axis, again, I don't start at 0, but I start at somewhere kind of low, I should be at 6 decibels, right? And then I should be at a frequency of infinity, or pretty high. I should be at about 20 decibels. So I should be doing this. Here I have 1, 0, and 1 pole. My pole was when s equals negative 5, or the magnitude of that when it's in frequency is just 5. And my 0 was when s equals negative 1, or in magnitude for frequency, that would be just 1. So when I actually get, here to 1, this is when this would start to slope up, because I slope up at 20 decibels per decade. I'm going to erase this. This is not pretty drawing here. This is 20 decibels per decade, and I would technically keep sloping up for forever, except for then at 5, I get my pole value, and that cancels out my slope that would have keep going up at 20 decibels per decade. It decreases it by negative 20 decibels per decade, so I get a flat value. Hence why I approach something as this goes to infinity. If it just had a pole, this would be going towards infinity and keep going. So that's how I can check my LabVIEW graphing of that. Also in LabVIEW, do note if you need to use it for any lab, if you have icons and particularly you haven't labeled them, please do label them, right-click, say visible, content labels, but you don't know how they work or what their inputs are, you can always double-click on an icon and then say Help, Show Context Help, and it will tell you all of the inputs and outputs that tells you what you need to wire into what. So that's really helpful, even if you can get some of them by hovering over their terminals, but the context help can be really nice when you don't know what an icon does, particularly if you're looking at someone else's LabVIEW programs in the future. So what do we learn from Bode plots? They show the amplification and phase shift, because our amplitude was like our magnitude and our phase angle, of a system output for sinusoidal inputs. Again, they were only working for frequency inputs, and I was looking at them at various frequencies. Hence why we graphed omega as our x-axis, so changing omega or changing frequencies. What happened to your magnitude? What happened to your phase? The shape of our Bode plots tell us information about stability of our systems, as we'll learn, and our time responses and much more, so they're very useful. It can also be useful for system identification. So as we'll see in the next video lecture, if we're given experimental data that gets us these Bode plots or our frequency response functions, I can come up with an equation for that transfer function that matches the data. And that's very useful to model stuff that you didn't know what it really did. Frequency response is, again, our steady state response to a system with a sinusoidal input. So you're not looking at what happened transiently, it's really in time, what is this going to keep doing? And for a linear system, our sinusoidal input will always generate a sinusoidal output with the same frequency, and frequency omega doesn't change, but my amplitude changes by now being my initial amplitude times the magnitude of my transfer function. And my phase will change by adding the phase angle of my transfer function. So my total output at steady state, remember, became amplitude times g of j omega's magnitude, sine of omega t, omega didn't change, plus whatever phase angle your transfer function ended up having for your frequency. Okay, that's the end of this video lecture.